Good morning, students. So today we are going to discuss about the problem related to direct and bending stress in Unit 3. Okay. Right now I'm sharing the problem. The column is rectangular in cross section. This of 300 mm by 400 mm in dimension. In dimension, the column carries an eccentric point load of 360 kilonewton on one diagonal diagonal at a distance of quarter quarter diagonal length from a corner. Calculate the stresses at all four corners. Draw stress distribution. Diagram for any two adjacent sides. So here they have given the rectangular section having the dimensions of 300 mm by 400 mm. Okay, in dimension the column carries the eccentric point load of 360 kilonewton on one diagonal at a distance of quarter diagonal length from the corner. So calculate the stresses at all four corners and draw the stress distribution diagram at any two sides. Okay. So this one we are going to do the solution. So given data. So breadth and depth they have given as 300 mm by 400 mm. So if I'm going to divide the section, y axis and the x axis. Okay. So we need diagonal length. Okay. So from the corner it is going to act. So B and B is available. Now the load is acting. That is P they have given as 360 kilonewton. Acting at acting at quarter length from corner. Okay. So if I am going to take this one as A, B, C and D and this is O. Now I have to calculate what is EX value and what is EY value. Okay. So let us go to the problem. Okay. Uh, so the eccentric load is acting at some point. We are going to take it as a E. Okay. So the eccentric load P is acting at point E. Okay. So here the length EC we have to calculate. Okay. So this is nothing but 1/4 length of the diagonal AC. Okay. So the length EC is equal to 1/4 of the diagonal length. Diagonal length. So here the diagonal length is AC. So 1 by 4 times of AC. Okay. Therefore, the diagonal length AC is equal to root under 300 square plus 400 square. So 300 plus 400 square is equal to 300 square plus 400 square is equal to 500 mm. So the length AC is equal to 500 mm. Next, if it is 1/4, therefore AC. Okay. Therefore, uh, the length EC is equal to, therefore the length EC is equal to 1 by 4 times of, that is 1/4 of length AC. Okay. So 1 by 4 into 500. So it becomes 125 mm. Okay. So from here to here, the distance is 125 mm. So the length is equal to 125 mm. Now this distance from here to here is also 125 mm. Okay. So from here to here, that is OE distance is equal to 125 mm. Now I need this height, that is EY and EX is equal to what? That I have to calculate. Okay. So the length OE is also 125 mm. 125 mm, that is also the length OE. Okay. Therefore, EX, eccentricity in X direction, which is nothing but E, we can give here as F and okay. So the length EX is equal to what? Okay. So here it should be like this. O E. So this is theta. So this theta we can calculate from the hole. Okay. So this is 300 mm and this is 400 mm. So from the tan theta is equal to opposite by adjacent. Okay. 400 by 300. Therefore theta becomes shifted tan as of 4 by 3. So the angle becomes 53 degrees 7 minutes and 48.37 seconds. Okay. Now I have to resolve into vertical as well as horizontal direction in order to get the distance of this. Okay. So now I know the hypotenuse, that is 125 mm. Okay. So from this, what is the length here? So this is f. Okay. So this is our ex distance and this is nothing but our ey distance. Okay. So ex. Okay. That is eccentricity in x direction, that is ef is equal to uh, oe. Okay, that is sin theta. We can go for sin theta is equal to opposite side by hypotenuse. Opposite side is equal to ef divided by hypotenuse oe. Therefore oe sin theta is equal to f ef. Okay. Therefore, the distance EF is equal to EX is equal to OE value is 125 into sine theta 53 degrees 7 minutes 48.37 seconds. Okay. So now 125 into sine, it becomes 100. It becomes 100 mm. Next is similarly the distance OF, that is therefore EY is equal to OF. So OF becomes cos theta. So cos theta is equal to opposite, sorry, adjacent by hypotenuse. So OF is equal to OE into cos theta. So it becomes EY is equal to cos theta. So 75 mm. Now the value of Ey and Ex are known. Okay. So by using this value, we have to calculate the moment and everything. Okay. So let us go for the further. So the moment about x-axis. So mx is equal to p into ex. Okay. So p value is 360 into 10 cube into ex value, that is 100 mm. 100. So it becomes 36 into 10 to the power 6 Newton mm. That is mx value. Similarly, moment about y axis. Moment about y axis. So my is equal to p into ey. So which is nothing but 360 into 10 cube into 75. So 27 into 10 to the power 6 Newton mm. My value. Now we have to calculate the value of uh, Ixx and Iyy. Okay, so moment of inertia about x axis. So Ixx is equal to b d cube by 12. So 300 into 400 cube divided by 12. So 300 into 400 cube divided by 12. So it becomes 1600 into 10 to the power 6 power 4. Okay. Similarly, Iyy about y axis. Okay. Then it becomes b cube d by 12. So 300 cube d divided by 12. So it becomes 900 into 10 to the power 6 power 4. Okay. Now let us move on to the stresses. Okay. So the maximum stress. Okay. Now like that we can go for something. Okay. So the resultant stress, the formula is equal to direct stress sigma d plus sigma b. So whereas sigma d is equal to p by a. Okay. Then sigma b becomes m. Okay. My into x by I yy plus mx into y by I xx. So this is the formula we are going to use. Okay. Now they have asked the resultant stress at all four corners. Okay. So now the resultant stress first. The resultant stress. Okay. First resultant stress at point C. Okay. That is this corner. Okay, so here in this corner the load is going acting here. Okay, so the maximum stress will be going to create here. Okay, since I already said the coordinates. Okay, plus plus, minus minus, plus minus, minus plus. Okay, that is x and y coordinates value. Okay, so based on that we are going to now with respect to the point O. Okay, so here it is y and here it is x. Okay, so based on this we are going to arrive. Okay, so for the first point the x value is 150 sorry, here x and y. Okay, so x value is 200 sorry, 150 and the y value is 200 So corresponding to this value, what is the value of sigma resultant? Okay, that we have to find out. Next, while coming to here, uh, the x and the y value becomes minus minus. That is very minimum stress. Okay, minimum stress, resultant stress. And while coming to the here, with respect to this position, okay, now, so all the corners here, here it is plus 150, here it is plus 200. When coming to here it is plus 150 and here it is minus 200. Okay, y value, and here it is both 150 comma 200 are in minus. Similarly, while coming to here, the value of 150 is minus, then value of 200 is plus. Okay, so based on this we are going to substitute here corresponding to the values of x and y. Okay, so at point C the x coordinate is plus 150 and y coordinate is plus 200. Okay, therefore resultant stress sigma r is equal to p by a 360 into 10 cube divided by area. So area 300 into 400 plus my. So my we have calculated that 27 into 10 to the power 6. 27 into 10 to the power 6 into x value is 150 divided by Iyy. So Iyy is 900 into 10 to the power 6. 900 into 10 to the power 6 plus mx. So mx is equal to 36 into 10 to the power 6. 36 into 10 to the power 6 into y value is 200. Then Ixx is equal to 1600 into 10 to the power 6. 1600 into 10 to the power 6. Now the sigma resultant value becomes, so 360. So 12 Newton per mm square. Okay. So 12 Newton per mm square. The value is in positive, so it termed as compressive stress. Okay, sigma R at point C. Next, at point B. Next, resultant stress at point B. So here plus 150 minus 200. So x is equal to plus 150 comma y is equal to minus 200. Okay, therefore sigma r is equal to 3 Newton per mm square. So this is also positive, so that is nothing but compressive stress. Okay, next at point A. So here both x and y values are in minus. So resultant stress at point A. So here x value is equal to minus 150 mm and y value is equal to minus 200 mm. Okay. Then the answer becomes sigma r is equal to minus 6 Newton per mm square. So the minus sign indicates tension. So sigma r is equal to 6 Newton per mm squared tension, compressive force and tension force. Okay. Next to resultant stress at point B. So at point D, the x value is equal to minus 150 mm, y value is equal to plus 200 mm. Okay, so x value is equal to minus 150 mm, comma y is equal to plus 200 mm. Therefore sigma r is equal to plus 3 Newton per mm square. Okay, so this plus indicates compressive stress. Okay, so this is the diagram, sorry, this is the value related to our stresses, resultant stresses. Now we have to draw the any two adjacent side stress distribution diagram. Okay, so A, B, C and D. So the value of C we have to. So at C it is maximum stress. Okay, 12 Newton per mm square. And at B it is 3 Newton per mm square. Both are positive. Okay, so from the uh, neutral line. So here it is 12 Newton per mm square. Both stresses are in compressive, and here 3 Newton per mm square. Okay. So this is the stress distribution in one side. Next one is uh, another side. So stress at point A is 6. Stress at point, sorry, 6 also in tension. Okay. So at D is, sorry. So at B is equal to 3 Newton per mm squared, and at A is equal to 6 Newton per mm squared tension. Okay. So here it is 3 Newton per mm squared, and here it is 6 Newton per mm squared. That is tension. Okay. So this is our stress distribution diagram.